Hi. So I wanted to say a few things. First, there's a mnemonic device for how you can think about wave function collapses and measurements and things like that. You can think of it as a mnemonic device. In the next part of the lecture, which is optional, I explain that it's not just an abstract mnemonic trick for remembering. It has a meaning to it. But anyway, so let's say that you have a pair of vectors. Let's say you have a coordinate system and you have a pair of vectors. You have a vector I hat and a vector j hat. And if you have any vector, let's say you have this blue vector, you can decompose that blue vector as a sum of something in the I hat direction plus something in the j hat direction, right? So you can say that the V equals some number A in the I hat direction plus some number B in the j hat direction. So you might say, well, what's that got to do with quantum mechanics? That's an analogy. And then again, it's more than just an analogy, but for now, think of it as just an analogy to a superposition of a wave function into two states, right? So this is the total wave function, and this is some coefficient A times psi1 e to the minus I e1 over h bar t plus B psi2 e to the minus I e2 over h bar t. All right. So in the analogy with quantum mechanics, the I hat and the j hat are analogous to the states of definite energy. This is like I hat, and this is like j hat. And a superposition state is one that mixes in a little bit of both. You know, how much both? Well, A and B determine how much of each. So if you do measure energy, the wave function collapses either into the I hat or j hat, or again, in the language of quantum mechanics, the wave function becomes just, it becomes, it becomes just this or just this. In mathematics, this is called projection. You project your vector either onto the I hat basis or j hat basis. So the operation of measurement is a projection. And after you've performed the measurement, the wave function will be just the I hat. It will not be A times the I hat, it will be I hat because it always has to be normalized, right? So you perform the projection, and then you adjust its magnitude so that it's always normalized, right? You see the wave function must always be normalized. So I guess if this is a circle of radius 1, after the projection, it has to be this long. So measurement is a projection. Let me implant that idea into your head. Or you could say that wave function collapse is a projection. Again, these I hats and j hats, they might seem like completely abstract representations of the wave function. And in the next optional lecture, I actually make the case that it's not an abstract representation. There's more to it than just a mnemonic device. But again, what I'm trying to say is that a measurement projects the wave function onto one of these bases, where you can think of the first circle thing as like the I hat basis vector, and the second circle thing like the j hat basis vector. Okay, you've performed the measurement of energy. After that measurement, your wave function is purely the I hat. Right, so that now your wave function after you perform the measurement of energy is now this, okay? So these bases, the I hat and the j hat, These are energy bases. Energy basis vectors. But what if now you choose to measure something else? Let's say now you decide, you know, now I'm going to measure momentum. So in the language of linear algebra, that means that now you will reproject your wave function, right? So after measure energy, get E1, and so that means the wave function is like I hat. Again, it might seem really, really abstract. I'm just saying that you can think of this circle thing as an I hat. Seems really odd, really weird. Okay, so if you've never had linear algebra, then it's just like a mnemonic device. But in the next video, I will try to make the case that it's more than just a mnemonic device. But okay, just follow the fairy tale. Just believe me, okay, that it's a measurement of wave function getting an energy, a certain value, and collapsing the wave function. It's like projecting the wave function into the I hat. Okay, but now I want to measure something else. Want to measure something else. Something else. Example, momentum. Which means that now you will project the wave function onto the momentum basis. In other words, you can get one of the possible definite values of momentum. And it's true that momenta can, they fall into a, usually they fall into a continuous spectrum rather than discrete spectrum, but that's technical detail, right? So you're gonna get one of the possible values of momentum, and the wave function after the measurement will be a wave function that corresponds to one of those possible values of momentum. In the language of these basis vectors, what you're doing is you're projecting your blue wave collapsed wave function, the one that's currently I hat, you're projecting it onto one of the possible momentum bases. So here's your momentum basis. Let me use a what's I prime hat. Okay, and this is right here is going to be J prime hat. I found that students actually can palette this language. Last quarter when I had that discussion in office hours with a student, he was like, oh, okay, well, everything just makes sense. So I decided, let me try to give you this kind of a perspective. Okay, so then project your new already projected wave function onto the momentum basis vectors I prime hat and J prime hat. So the momentum basis vectors, just like the basis vectors I hat and J hat, these are states or wave functions that correspond to definite energy. So I hat is a wave function that has energy 1. J hat is a wave function that has energy 2. I prime hat is a wave function that has momentum P1. J prime hat is a wave function that has momentum P2. This is wave function with momentum P1, and this is a wave function with momentum P2. So now I'm going to perform a momentum measurement. After I've performed the energy measurement, I'm going to perform the momentum measurement. Notice that you can rewrite the blue psi as a linear combination of these new basis vectors. And so I can say that blue psi is some kind of another coefficient, a prime times I prime hat plus b prime times j prime hat. Perform the measurement. You're going to get either momentum P1 or momentum P2. The probability of getting P1 is the square of the amplitude of A prime. Okay, A prime is a complex number. It has a magnitude or amplitude, and you square it. That gives you the probability. And the probability of obtaining P2 is the square of the amplitude of B prime, or square of the magnitude. If you do get P1, then after the measurement, the wave function now collapses to this thing. So it collapses to I prime hat. Okay, so measurement, get P1 with probability prime squared. Now the wave function collapses, or it gets projected onto I prime hat. So now, instead of this blue thing, the wave function now becomes here's your new wave function. So every measurement that you perform recollapses the wave function or reprojects the wave function onto a different set of basis vectors. That's a linear algebra way of thinking about measurements, and it's not a coincidence because behind everything I've been talking about this week is linear algebra, linear algebra, linear algebra. In the next video, I make it even more, I spill all the beans, but you don't have to watch that lecture. In fact, this is also kind of optional. It's just to, I'm not going to quiz you on this. I just want you to give another, I just want to give you another perspective. So the wave function was this blue thing. You've performed the measurement. You've collapsed the wave function onto one of the basis functions or basis vectors that correspond to a definite value of energy. Now you make a measurement of some other quantity. That other quantity has its own set of basis vectors. And when you do perform the measurement, you will recollapse the wave function onto one of the basis vectors of that other quantity. What are these basis vectors? These are a set of wave functions or vectors that correspond to a definite value of some particular quantity. So I and j are wave functions that correspond to definite value of energy. When you do make an energy measurement, the wave function will be projected or it will collapse onto one of those. So here it is, it has collapsed. Now you decide to measure some other quantity. Okay, that other quantity can take on certain values, and for each value that it can take on, the wave function will be one of possible basis wave functions, right? So if I and j are states of definite energy, I prime and j prime are states of definite momentum, for example. When you do measure the momentum, the wave function will become one of those new basis wave functions, with probabilities given by the square of the magnitude of each of those coefficients. So let's say you do perform the momentum measurement, you get P1. That means after that, the wave function has been reprojected onto the I prime hat. The next thing you do is you measure angular momentum. Angular momentum has its own set of basis wave functions, meaning that when an angular momentum takes on some particular value, L1, L2, L3, the wave function will be one of those basis wave functions. Each of those basis wave functions has a definite value of the moment of angular momentum, and so on. You project. Next, you measure something else. You measure, I can think of some other physical quantity. There are many. After that, the wave function will be projected again onto the new set of basis vectors. So this is, I don't know, maybe if this is confusing you, don't be scared, don't worry. I'm not trying to scare you. I'm trying to give you another perspective, and in the next video I go deeper into that perspective. So this is point one. Point two. Now I want to use this opportunity to mention some issues that I'm seeing in student thinking. Students still think in terms of a classical notion of motion. They ask me something after you've performed the measurement, the wave function collapses, and how does the particle move after that? The particle, forget the idea of particle moving. That's a classical notion of a pebble following a trajectory, okay? All there is in between the measurements is a wave function. You measure the position, you've collapsed the wave function. Then you release the particle. So you measure position, collapse the wave function. Okay, so after that, you release the particle. The wave function begins to evolve. What determines how it evolves? The Schrodinger's equation determines how it evolves in accordance to Schrodinger's equation. In classical physics, the thing that fully describes the particle at any moment in time is position and momentum. How do position and momentum evolve? They evolve according to the Newton's equations. In quantum physics, the thing that fully defines the particle, that's what I mean by a state of a particle, that fully specifies the particle at any moment in time, is not position momentum, but it's a wave function. What determines how the wave function evolves? The Schrodinger's equation. You see, it's an analogy, it's a parallel, it's a different viewpoint. Wave function is a strange abstract thing. It's not a particle. It's a quantity that from which we can get statistical, from which we can get predictions about statistics of the outcomes of any measurement that we want. That's what a wave function is good for. Okay, it begins to evolve, and the way it evolves is, this peak, it will broaden. Okay, it broadens, initially it broadens really fast. And this is somewhat analogous to diffusion. If you have a concentrated dye of chemical, initially, after you put a blot of chemical into water, it spreads very fast and then it spreads slower. It's diffusion. There are some analogies between the Schrodinger's equation and diffusion. Just a rough analogy. And it might get, it might get certain wiggles. It might become something else, and then time t after, time delta t after releasing, the wave function will become something else. So this is now the wave function time delta t after releasing it. You've measured, you've collapsed the wave function, then you release, the wave function evolves. And so what this means is that now if you measure, let me say that this is squared, right? So now if you measure the position of the particle, you might get this, or you might get this, or you might get this, or you might get this. This is very inconsistent with the notion of trajectory. In trajectory, the position evolves smoothly. think what would happen if you keep measuring position every second. You measure position, you collapse the wave function, you catch the particle here. Oh, I caught the particle. You release. Okay, and now you measure position, you get a particle here. Next, you release, you measure position, you get a particle here. You would get kind of a somewhat stochastic trajectory. And if you were to make measurements more often, your trajectory would become more and more jagged and irregular. So it's not, trajectories are not very compatible with, your classical notion of trajectory is not very compatible with quantum mechanics. For now, forget trajectories. Okay, there is a way in which trajectories do make appearance in quantum mechanics, but in this introductory way of teaching quantum mechanics, just repeat the mantra. In between the measurements, all there is the wave function. When you perform the measurement, you collapse the wave function. So the wave function evolves in two ways: smooth evolution in between the measurements, and instantaneous collapse upon the measurement. You make the measurement, the wave function collapses. You release the particle, the wave function evolves smoothly in accordance to the Schrodinger's equation. Okay? That's point number 2. Okay? And I just remembered point number 3. Operators, operator math. So I discussed thing like this, right? So what does this mean? This is a sandwich in which you put the wave function, you conjugate it, you put the operator could be multiplicative like x, or it could be differential like ddx, and you operate with that operator on psi. So this means that O operates on psi. So for example, you have psi star times partial derivative psi. And what that means is that you take the psi, it operates on the psi, you get some other function, and then you multiply it by the conjugate and you integrate. You cannot move operators around, okay? Okay, so this does not equal, it's not a function, it's an operator, it does something. This is no, no, no. You can't just like move operators around. So some students do this kind of thing. In fact, this makes no sense. It makes no sense to say this, the dx here. What is this? What is the ddx operating on? It's flapping in the wind. It makes no sense. You cannot move operators around. Wherever you place them, that's where they are. And what sits in front of them, this thing right here, gets hit by that operator. Once it gets hit by the operator, you've operated on the psi, it becomes some other function, phi. And then you multiply that by the conjugation of psi star. You can't move operators around. Operators have to operate first, okay? If it's a derivative operator, it has to differentiate what sits in front of it. Then it becomes a different function. Then you can move that other function around. So for example, you can say, this is okay. Right? This is okay. So this does equal to, this is okay. But this is not okay. You can't move operators around. Operators operate on whatever sits right next to it, on whatever it's hitting. This is okay, this is not okay. Because this is a single object. This is a single object. Okay? I witnessed this kind of thing with students, so I just wanted to bring that up. In summary, this is a little pointer about operator math. This is a little pointer about getting out of the mentality of how does the particle move in between measurements. In between the measurements, what evolves is not the position of the particle, but the wave function. And this is another perspective on wave function collapse seen in the linear algebra way as a projection, as a operation of projection. But if this bothers you, don't be afraid, don't worry about it, just forget it, okay? So some students might appreciate it, and some students might be kicking and screaming, and then just don't worry about it, no need to kick and scream. But point number 2 and point number 3 are pointers that are in response to what I'm seeing and hearing from students, okay? Okay, part 3 of, so this part 1 is a good lead into the part 3, which is a completely optional lecture. If this class is giving you a headache, notice I try to have a parallel track. The minimal information and then the optional information. So if you're a physics major, if you just want to get ahead and learning quantum mechanics, please watch optional parts. But if the class is just giving you a headache and you're just doing it because you have to, I appreciate that, then you don't have to watch the optional lecture, okay? And even this part 1 is kind of optional. Don't worry about it too much. I won't quiz you on it, okay? It's just another perspective, so you can see the matrix from another perspective, from the linear algebraic perspective, okay? All right, I'll see you soon.